So we're very happy to have Jonathan Heckman for the last talk of today. So please.
Okay, so first let me say thanks very much to the organizers for putting this very nice meeting together. I've really enjoyed a lot of the talks, and also for the invitation to come and talk. I'm going to be talking about things related to symmetry TFT. I don't think that needs any introduction here. And the motivation is to kind of see whether there's potential generalizations that naturally arise in the context of stringy realized QFTs and structures that appear in string theory, extra dimensional geometry, and how they might motivate certain kinds of generalizations of SymTFT framework. So I realize this is a pretty broad audience, so I'll try to state my conventions because they may not be uniform across all groups. So let's go. Does it go? There we go. Okay, so here is a sandwich. Well, this is what I'll mean by a sandwich, a cheese sandwich. And I'll also be talking about this over here. This is a bit more regional, probably not known to everyone. So this is referred to as a cheesesteak. So this is kind of a fattened or a mutated version of a sandwich. And so hopefully you'll see the sense in which the original sandwich is getting mutated by the end. Okay, here it is, so you can compare the two. So what I'm going to be telling you about is based on some work, some of it which has already appeared. Actually, the primary content of the talk is based on a paper which is not out yet, which will hopefully be out sometime next week. But I'll briefly just mention a few of these as just some other potential generalizations one might consider. But my main focus will be on this one down here, which hasn't appeared yet. Okay, and I'm sure I missed some references, and I'm sure I also missed references to talks and also to papers, so I'm sorry about that. So what is the idea? The idea is we're going to be starting in kind of a complicated ultraviolet system. We're going to imagine we have something like quantum gravity or string theory on a particular background. And what we're going to do is we're going to take various kinds of limits to kind of strip out some of the complications of this complicated system and hopefully arrive at an interesting looking effective field theory or quantum field theory and study some of its properties. And the main idea is to, in some cases, if we have a particularly favorable background, to use the geometric properties of that background to say hopefully interesting things about low energy field theories that we get via this arrow of implication. Okay, so again, terminology, so we're all on the same page. What I'm going to mean by d dimensions is going to mean space-time dimensions, so I'll have one time and d minus one spatial. So here, let me just give a quick example of the kinds of things that will arise. So M theory is some 11-dimensional setup that we're going to start with, and it allows us to kind of engineer very interesting quantum field theories. So this one is perhaps the least interesting of the ones I'll talk about, but this provides us with a way of talking about how to engineer a 7-dimensional Yang-Mills theory with some amount of supersymmetry. That's living on the 7-dimensional spacetime here, and then we have some particular singularity here. I might forget to refer back to it. So it'll be just some conical geometry like this, and the idea is that this gives us some SUN on the Yang-Mills. And for now, I'm going to be a little bit vague about what kind of group I actually got. I'm just going to specify the Lie algebra. And then the group action has this one fixed point at U equals V equals 0. Okay, so this gives us some 7-dimensional Yang-Mills theory. So the idea is that particular geometries can do interesting things for us in terms of engineering things. Now you might say, well, I know about this theory, what do I need geometry for? And maybe you don't. But here's a more complicated case, which resists a kind of nice kind of description in terms of Yang-Mills theory. So for example, if we kind of go to a higher dimensional singularity, for example, C3 mod Z3, so here I've listed also the group action. There's again a fixed point at the origin at U equals V equals W equals 0. And it's known since a long time by various folks in the room that this thing produces now a 5-dimensional conformal fixed point with some minimal, with supersymmetry. So here it is. I'm writing these ones on the board because I'll be coming back to them several times. W. So the key idea in both of these is that there's kind of a conical geometry. There's a single tip of the cone, there's kind of our flat space, which is a spectator, and then there's some boundary geometry over here. Okay, so as I've already mentioned, we can use these kind of stringy backgrounds to build interesting kinds of field theories that are typically hard to understand through other methods. In a particular, quote unquote, I'll say just non-Lagrangian field theories in, say, 5-dimensional and 6-dimensional fixed points, and then their compactifications produce a whole host of interesting strongly coupled theories that are sometimes very difficult to study using other techniques. So sometimes we don't even know what the Lagrangian is. Nevertheless, in some cases we know some properties of this based on the geometric starting point. And in particular, one of the themes of the last few years is that we can use geometry to also identify various kinds of generalized global symmetries in these settings. Another very natural question in this setting, which is kind of very well geared up to this, is you can take that local cone and imagine gluing it into some kind of compact geometry. And this provides a way to talk about recoupling these field theories to gravity. So after we take these scaling limits, we can say, what if I didn't take the scaling limit? What would I do? Okay, so here is the basic idea. I think it's already been sketched in several of the talks. But this is the picture, at least as we understand it right now, in kind of the basic setup. We have our singularity here, and then if we're interested in various kinds of defects, we take certain kinds of branes which wrap from the boundary of the space to the tip of the cone. The topological, and they look like this in the space-time. And then they're linked both in the quantum field theory directions and in the kind of boundary topology. This enacts a corresponding Aronoff-Bohm phase to produce the corresponding symmetry operator, which acts upon the defect. And again, I'm going to kind of jump over some of the details in light of time and also in terms of composition audience. But you can basically do some kind of dimensional reduction for just the kind of topological subsector of this more complicated system after taking suitable scaling limits. And what you land on very beautifully is something that looks like the symmetry TFT picture. So the physical boundary condition over here is supposed to be over here, this tip of the cone. And then the kind of topological or gapped boundary condition is over here at the boundary of X. So this is a pretty nice picture. And I think there's a fair amount of evidence that it does the right things in cases where we kind of can cross-check it, where we have a Lagrangian example. But it also extends it to cases where we may not have a cross-check for what the SymTFT is. So this provides a machine for basically spitting out answers for what the SymTFT is going to be. Okay, so I don't need to say this for this audience. I probably don't need to say this. It's best established for finite symmetries, and there's subtleties that have been proposed in the literature recently for how to deal with the case of continuous symmetries. And sorry if your favorite paper doesn't appear here. There are some kind of distinctions, subtle distinctions between how people in the various papers have treated different kinds of boundary conditions where they want to deal with compact or non-compact gauge groups, those sorts of things. We'll try to take some kind of middle ground where we'll see, depending on how we regulate the geometry and how we take these scaling limits, how some of these different approaches come out. Okay, so here's the basic idea. And then what we're going to be doing is considering various kinds of generalizations of SymTFT motivated by geometric structures we naturally see. Okay, so here is the basic setup. Rather than drawing this kind of complicated thing with two sides and a lot of things, I'm going to be generalizing that in some ways. So here I'm going to mean exactly the same picture I had before, but I've compressed some of it down. So I have some d-dimensional relative field theory over here, some boundary conditions over here, and then some one higher dimensional bulk. So the interval now is just one higher dimension relative to what we were talking about previously. Okay, so how might we imagine generalizing this? So again, I'll be a little bit loose for now about what I'm talking about in terms of SymTFT, or possibly some symmetry theory, if it's corresponding to, say, some continuous symmetry. And correspondingly, I'll be a little bit loose about the boundary conditions in play. Okay. So here are some top-down generalizations. Again, I'm going to focus on just one of these, but at first I'll just kind of list a few that you might be interested in or motivated by these kinds of stringy considerations. One is, often we have not just one singularity, but multiple singularities. And you might ask, what would that correspond to in the context of the SymTFT framework? What you actually end up getting in these cases is junctions built out of symmetry TFTs. That's each of these little segments here. And there's some script J here, it's mathcal J, which is typically a fairly benign theory. Its role in life is to essentially glue all the boundary conditions from the different SymTFTs together. So for example, this one could be a Z mod N gauge theory, this might be a Z mod M, and this might be a Z mod, say, N plus M. And we have to find identifying all the fields across the different pieces. That's the role of the junction.
Sorry, is this just describing a theory which has this tensor product of full symmetry?
It's a product of the full
of
symmetry.
the two?
No, you can get it, for example, if you started with like say SUN plus M and considered like adjoint Higgsing down to SUN times SUM at the level of Lie algebra, and then you'd say, now tell me the spectrum of line operators under that Higgsing. That's a...
It's the tensor product of the two, no?
Well, no. It's a leading order. Okay, so another interesting generalization, one I won't talk too much about, is you can even consider non-supersymmetric backgrounds. These typically, at least in the stringy context, have various instabilities where you can kind of smooth out, in some cases, what's happening here. And what you often get in these cases is not quite the original SymTFT picture, but something that also involves time. And here I've drawn how that causal structure appears in a particular example where this is really supposed to be thought of as a Penrose diagram. And you can track what's happening again to the boundary topology as a function of on future null infinity, and it moves around. So it's a bit more complicated than the kind of classic SymTFT picture, but it provides you a way of understanding instabilities and possible symmetry restoration at critical values of coupling. And then lastly, the one I'll talk about, these cheesesteaks. So you can see it's kind of a fattened up thing here. It's dealing with a different kind of generalization, one in which this projection down off of boundary X to include the radial direction is not going to quite work if we just stick to the original story. And the reason it doesn't work is because the singularities are now no longer isolated at the tip of the geometry. They're spreading out in this direction. So if we look radially, then there's a singularity that's also extending out all the way. And again, the idea is that there's some integral of a boundary. And what we're going to land on is something that actually jumps up in dimension by 2 units. That's the simplest case. You can start refining it and doing higher dimensional refinements. But this is at least what the geometry is suggesting is a refinement. So I'll explain how this picture comes about in just a moment. But this is where I'm going to spend most of my time. So the original relative theory hits here. It's coupled to some other systems here. And those are in turn coupled to another system here. And it might go on for a while. And again, also the boundary condition itself is getting spread out a little bit more.
So BD plus 1 is gapped?
Yes. Yes. BD plus 1 is going to be gapped. Geometrically, actually, sometimes you want to include U1s or free factors like this, but in the simplest cases I'll talk about, it's going to be totally gapped. TD plus 1 is not going to be gapped. I'll give an example of that. And in the simplest situations, SD plus 2 is going to be gapped. So the point is that if you just try to follow the very nice procedure you had in your paper with these flavor singularities sticking out, then you have to work a little bit harder to kind of get a SymTFT straight from dimensional reduction. And so part of the idea is to say what happens in these more complicated geometries. Okay, so I'm going to refer to these as kind of nested relative symmetry theories and so on. So again, the idea is that the big issue that we'd like to deal with is that there's these flavor singularities, these additional singularities which are not just trapped at the bottom, and they actually extend all the way out to the boundary. And this poses complications for how we read, say, the defects, the symmetry operators, and also the symmetry TFT from these kinds of setups. So here's an example. If you have, say, intersecting branes, these things support gauge theories by themselves, just strings stretched back to themselves. These dictate fluctuations of the branes, and they often have matter that's trapped at kind of the intersection between these two. Here's a cartoon picture of that, where we're just focusing on the lower dimensional bit. We have some matter, and it's transforming, say, in the fundamental of SUN and the anti-fundamental of SUM. Maybe you have more matter. That depends on the details of the brane setup. So we can, of course, confine our attention to just this little dot here and the physics of that. But we might want to consider it from a higher dimensional point of view and say, well, what if I had also included the dynamics of the branes? Maybe I want to think about it as some higher dimensional gauge theory coupled to some things stuck at some particular location inside of that higher dimensional gauge theory. So that's an example. Another example, and one I'll return to a few times, is this one down here, which has been recently heavily studied in the context of 5D CFTs and their symmetries. This one has the interesting property that there's a fixed point locus like this, and if you look at the singularity, it can be interpreted as an SU2 flavor symmetry. So the boundary topology is some S5 mod Z4, but that S5 mod Z4 has some singularity due to the group action we have from this particular Z4. Okay, and here's just a little bit about just some review of some things we think we know about these systems now. If you try to read it off, if you remember this picture that I had down here with this C2 mod Zn, I said that would give me an SUN Yang-Mills theory. It turns out you can interpret that in this case as giving you an SU2 Lie algebra for the zero form symmetry. If you neglect things like the R symmetry and the space-time symmetry, then this looks like an SO3 flavor symmetry, so you quotient by a Z2. And it turns out that there's also a Z2 one-form symmetry. And in fact, these get entwined into a 2 group. I'll explain how that comes about from this cheesesteak picture a little bit later. Okay. Lastly, one might want to consider a quantum field theory, maybe with some other defects stuck in it, and you'd want to know about the symmetry TFT for maybe this defect, the bigger thing, and then all the whole thing together. Okay, so let's do building a cheesesteak from the bottom up. This is motivated by stringy considerations, and so there's going to be a few choices, but they seem to be dictated by things we have coming out from the top-down point of view, but I'll present it in this order just so I don't lose as many people as quickly. Okay, so this process that we had with a d-dimensional system like this, we decompressed it basically to a relative theory here and then some boundary condition here. Now, what I'm going to do is I'm going to view this SD plus 1 as we know in the string context, is basically being obtained from taking some kind of limit of some possibly more complicated d plus 1 dimensional system. So what I'm going to do is think about all the different scales and couplings, whatever they may be, and I'm going to put them back in and kind of view the thing that we had as being this more complicated field theory. And maybe I'll take that scaling limit at the end, but I need to potentially just keep it arbitrary for now, and then at the end I'll try to take scaling limits. Okay, now, since I've handed you a new field theory, I can treat that in its own right and say, what would happen if I decompressed that thing by itself? I'll give you an example in a little bit, but this is something for sure I can do if this is just a field theory in its own right, and I'll just decompress again. So now I have some higher dimensional SymTFT for that thing, and its relative theory here, and its gap-free piece over here. And now you can see that I can just keep iterating the procedure over and over again. I'll deform this thing in the middle, decompress that, and keep going until hopefully I wind up with a gapped system in however many dimensions I have to go. At least in all the contexts that come from these top-down stringy constructions, kind of guarantee that there is kind of a limit because we run out of space-time dimensions, if you like. But I don't know a general proof without that. Okay, so here is the kind of general picture if we keep iterating the story, and then we keep going until we hit some finite field theory. Okay, so here is the picture. Now I want to bring back in the corners that we had previously. So imagine we now stick our theory. I've suppressed the kind of coupling dependence, but it's still there if I want. And I'm going to decompress it, but I want to take into account the fact that I had these boundaries for this d plus 1 dimensional system. So I'll fatten it up a little bit in the middle. Now here, actually we have those junctions that we were talking about earlier in the context of tree-like symmetry theories. Those are not completely topological. They're usually just some free theories that enforce different kinds of boundary conditions between the different segments. So what we can see is that we're growing out this kind of bulk here, and then we have some BD plus 1 here and some TD plus 1 here. So B again is, the script to B is going to be gap, T is going to be some relative theory. And we're going to keep pushing it out. And then what ends up happening, and this is again motivated by the geometric side of the story, is that the original boundary condition can turn out to get a little bit spread out over this, faint region over here. My main emphasis for today is really going to be here and here, but of course I have to tell you what's happening with the boundary conditions here in order to fully specify things. Okay, so here's an example of how defects are now produced. I can start with something that kind of stretches from this boundary over here, goes to the gap side, and then just stretches along that d plus 1 dimensional side. That's one thing I can for sure do. I could also do the reverse and consider something that starts in the other boundary condition and go the other way, down here, to get another class of defect. Or I could have something that kind of gets shared between the two. So it kind of stretches across, passes through the corner, and then comes out the other side. All of these things can, in principle, happen. So in order to kind of tell a proper story, I now need to talk about various kinds of boundary conditions for what happens with fields in the bulk as I push them over, say, to one of these boundaries, say BD plus 1 or TD plus 1, and then down further into the corner. Okay, so let me now return to an explicit example that might have been a little bit too vague. Here, this is the picture we're going to have geometrically. This is a particular 5D CFT. It has this SO3 zero-form symmetry with it. And what we're going to wind up with is 5D corner theory, 6D kind of gap theory here, and then a 6D relative theory here, and then a fully gapped 7D theory here. what do we get in this B6D? What we're going to get, it turns out, is something that looks like this. And I'm going to write down this whole thing as a Z mod 2n set of valued fields. The people who know this theory well will recognize that actually I've written down what's called quote-unquote naive one-form symmetry. Turns out that the actual one-form symmetry is valued in Z mod n rather than Z mod 2n. We'll see how that fits in the story. Down here, we're not going to have a gap system. We're going to have a Yang-Mills theory. The one we get if we just straight reduce involving the C2 mod Z2 will just be our friend, the 7D Yang-Mills. But there's going to be a further when we go to this SymTFT picture, where we reduce on a further circle to produce actually a 6-dimensional Yang-Mills theory, one that actually has a position-dependent gauge coupling if you track it. Okay, what do we have in the bulk here? This is going to turn out to be a set of Z2 valued fields. And again, I'm being vague with the coefficient here. I'll put all the numbers in just a moment. But we're going to have a Z2 here, in other words, a Z mod 2n here, and an SU2 here. Okay, so the first one is I have to tell you about how the Z2 fields restrict onto here or vice versa. And so in particular, what we'd like to know is if I have defects that are defined over here and they're just kind of attached intrinsically to this boundary edge, can I ever kind of pair them up and pull them off into the bulk? And I can indeed do that if I pull them off in pairs. One can check that geometrically. That gives rise to a particular short exact sequence, like so. So this is what we would refer to as kind of the quote-unquote naive one-form symmetry, Z mod 2n, and it turns out that the actual one is Z mod n. And the Z2 here is really just this Z2 here. Let's do the same thing for the other boundary. We have an SU2, we have another short exact sequence we can write down. And in this case, the Z2, our friend the Z2, which we already talked about previously, shows up in the other side. And it's what's allowing us to talk about how various kinds of lines, or flavor symmetry lines that we have, will get paired up and possibly pull off here, or get pushed into the corner. Putting it all together, what we get is, one can check, and this statement here was kind of known from other points of view geometrically, earlier, and also field theoretically earlier. But the point is that we can now see it coming out from these kinds of boundary conditions of this higher dimensional, 7-dimensional TFT in this case, and its various edges and corners. We can assemble it all into a long exact sequence, and this is known to tell us about kind of the two-group structure that we have in this story. Okay, and more generally, now I'll just abstract away. If I had my favorite naive G tilde, I guess some of these did not correct it. It's supposed to be script G tildes everywhere, but okay. We have the naive one-form symmetry, the naive flavor zero-form symmetry, and they all get corrected by this common script Z, which is here, and the various boundary conditions I was telling you about, again, assemble into two short exact sequences, or alternatively, in terms of one big long exact sequence, telling us about the two-group in this case. So now I've told you about how we think about it from a bottom-up point of view, but now what I'm going to do is, so some of this was kind of motivated by various considerations. Now I want to explain a little bit more about where we got this guess from, and motivated a little bit more from geometric structures we can see on top down. So again, here's our basic setup. What we have is some Yang-Mills theory plus ... when we have these flavor symmetries floating around. And then the various kinds of limits we have to take, which are fairly subtle, and the different points of view, as far as I understand in the literature, involve different choices of limits one takes for how the gauge coupling is switched off and how you decouple, say, the bulk from the boundary to leave yourself either with free vectors or a fully gapped system with a non-compact gauge group. You have to take some kind of scaling limit, and depending on what you pick for the radial profiles, you might get a different answer for how the boundary condition is behaving, but they all kind of start off life in this way, and then you zoom in and take some limit. Okay, so now what are we doing geometrically? Well, the main idea is to kind of cut apart the geometry, and so we can just isolate piece by piece the different kinds of singularities that we have. So we have this unpleasant singularity here, and if we didn't have it, we could just follow the prescription, which was already explained several times, where we just dimensionally reduce on the linking boundary X to produce the corresponding SymTFT. That's a nice procedure that works in those cases. So what I'll do is I'll just cut that thing out, and I'll talk about a space I'll call X delete K. K is just some tubular neighborhood enclosing this singular piece. Now, I might also just be interested in the singular piece by itself in its own right. I'll call that X singularity. That thing comes with its own boundary topology. So for example, in the C2 mod Zn case that I've been talking about, the boundary topology would just be some lens space, some S3 mod Zn. So that piece is in there as this little purple dash piece, and then that piece is being glued in to a more complicated geometry by piecing these together. Okay, so here we go in our particular case. I don't have a better name for this, so I'll just keep it as X delete K. So we just have C2 mod Z2 in our favorite example, this 5D CFT. We have a C2 mod Z2, and it has this S3 mod Z2 at its boundary. Okay, so let me first focus on the SymTFT I would get if I just paid attention to this little singularity by itself. So this is again a case Iñaki, for example, reviewed. We can just talk about that thing and what kind of SymTFT we would get for that. In this case, it'll be some 8-dimensional bulk system. We have some 7-dimensional theory here. And in this case, we just have some SU2 super Yang-Mills. And then the bulk system here is some Z2 theory set like so. Now let me go back and do the other part, this piece here. This is also going to be producing for me something. So I've deleted all the singularities that were contaminating the bulk, so I still just have this isolated piece here. And topologically, this is a fine thing for me to talk about. So I can again apply the procedure that was already talked about, but now with this reduction, with this tubular neighborhood cut out. Let's do that. What do we get in this case? You get something that's valued in Z mod 2n. So remember, that's the naive one-form symmetry answer, having Z mod 2n values, and the Z2 in the bulk is correcting it to the Z mod n. And you can read off again directly from the geometry these coefficients. Here I've indicated what happens when there's this quote-unquote 1/6 refinement that comes from looking at the n CHG term. But if you don't like that, you can just multiply through the whole thing by 6, and you have kind of the unrefined answer. And you can do various things involving various kinds of other kind of anomalies involving mixed anomalies. I'm not talking about that here, but you can read off even more data directly from this cutting and gluing procedure. Okay, so here is our cheesesteak. And here's the way it looks in terms of this. So we have some gapped piece over here, some gap piece over here, and then this relative piece here. Okay, so I'm almost out of time, and I'm almost out of slides. So here's the picture. Roughly speaking, the idea was to apply the same symmetry TFT picture we were talking about earlier, taking some boundary of a boundary like this. And then what we saw is that kind of the geometrically motivated answer we got was this kind of bigger mutated sandwich, if you like, where we had some gap piece here, some relative theory here, and then some corner theory here. And of course, if this thing didn't turn out to be gapped, you can write down more complicated systems where after one step of refinement, it's still not gapped. You can keep going and produce something even more, even higher dimension. So one of the things I didn't really talk too much about is non-supersymmetric backgrounds. We now know various techniques for reading off from geometry the generalized global symmetries we get in those backgrounds as well. Those have the interesting property that they have some time-like dependence in it as well. So it's another kind of generalization. Can we combine it with this cheesesteak? So cheesesteak, I guess, which is getting eaten. And then another very natural question is to extend this to kind of more general kinds of backgrounds. So in particular, a lot of this relies heavily on having geometry, extra-dimensional geometry. But of course, from a purist point of view, there's many other backgrounds in string theory that don't necessarily have as clean a geometric realization. What can we say about those systems? So that's another thing we're thinking about extending to those cases as well. Okay, I have some slides for omissions and things I jumped over too quickly, but I'll stop here. Thank you.
Any questions? Okay.
Thanks. Where in the cheesesteak you see the delta B is stock W2, like the actual two group that this is really a non-trivial extension. You see it as the sequence, it seems, but how do you actually see the two group?
Well, if I gave you the two short exacts, that's equivalent to telling you the long exact. So.
Yes, but then in a specific background, you still need to check that it's really there. It's sort of that, you know, the actual flavor symmetry is SO3 and there's a really non-trivial box theme.
Oh, yeah. I mean, that follows though from the looking at how the line.
Right, so you still need to do that, right? So
Absolutely, yes. So you still need to do that, but the point is that, here, let me go back a couple of slides. Yeah, that's the part I kind of, you have to specify, that's the wrong way. Yeah, you have to specify all the defects, all the symmetry operators and what they do. So here I've only drawn the defects, but there's also the symmetry operators and linking with them. All of that has to be checked as well to specify or to answer your question. I jumped over that, but yeah, it's there. Yeah.
Any other questions?
Okay.
If not, let's thank Jonathan.